talk has started. This is a document we've been waiting for possibly years, depending on where you want to start counting. But definitely when they had the drafts for Chem come out, which was last year, they said, we're going to give more guidance on how we want on using chems, because I think Chem FIPS 203 was the first chem FIPS. They said we're going to have a document that eventually became named Special Publication 800-227 about using chems, and this is it. So I have some vague ideas of what's going to be in here, but it's mostly if you care about FIPS, if you care about Nist stuff, raise or lower. I'm at 10%. I'll go down even further. Being kind of quiet here because we have a puppy and the puppy's sleeping. So if you want to see the puppy, go check out my Blue Sky. Actually, here's a concept. Bring it. Yeah. I don't want to wake her up, otherwise I'd be showing her off. But she's adorable. Okie dokie. So I literally been holding off on looking at this, so you get like a live react. Ooh. Interesting that way. So one of the things that we definitely want guidance on is that Nist has been basing all of their compliance stuff based on other special publications about how to do KDF stuff, how to derive secrets, and all of them have basically said, if you're going to put something through a KDF or derive other secrets from it or whatever, put the like FIPS or Nist secret that we derived from a thing first. So if you're using if you're using P56 or you're using RSA or something like that, from literally left to right for the pre-image of something you're putting through a key derivation or, whatever, they want the bytes for the, P56 shared secret first, and then anything else you also want to append after. So if you've seen anything on the internet about Z concat T or Z equals Z prime equals Z concat T or something like that, that's what that's all been about. So people who care about FIPS compliance, they've basically been very careful to put anything that needs to be the FIPS compliant secret part first, from left to right, those bytes first, and then anything else afterwards. So if you care about hybrid post-quantum stuff, people have been putting P56 in that position for a long time, and then anything else afterwards. But now we have a FIPS for post-quantum, so now some people have been trying to put Chem shared secret first, and anything else after it, like say, X25519 or something like that, classical secret. There have been rumors. People have been saying, like, it's kind of annoying that we're hamstrung this way, of like we have to put the FIPS compliant shared secret in a specific position. It'd be nice if we had more fluidity, because it really doesn't matter from a security or cryptography perspective. It's just kind of like a put the thing in the place we expect it to be so that everyone is sure about where we expect things to be sort of thing. So that might be the only thing that, well, actually, okay. I care about see if they say anything about that. I care about if they say anything about binding properties. We'll see if they do. We'll see if they say anything about hybrid versus not hybrid, what security properties they mention, maybe key derivation, but they might not say anything about that because they have a FIPS for that. We'll see. I'm gonna move some things around. Let's see. Oh, is that why things are weird? Yep. Chem, shared secret. This chart describes basic definition, properties, application, and kind of recommendations to implement these in a secure manner. Okay. Patent stuff. Who cares? Blah blah. View theoretical security requirements, compliance, graphic data, establish key establishment. Confused with encapsulation. Derivation confirmation. Multi-app hybrids. They're just using all the terminology. Okay, examples. Hybrid. Oh, HVK. Oh, hey. In CPA, in CCA security. Oh boy. And Mac algorithms for key confirmation. Okay then. Okay. Establishment. Yeah, SP 856. 56 PR2. Yeah. Yeah, post quantum. Yeah. Yeah, key encapsulation, not to be confused with key establishment, not to be confused with key exchange. Words are hard. Yep. Chem. Okay. Yeah, at the time of standardization, not providing extensive guidance and definitions, properties, applications. Okay, all right. Guidance for current and future standardization of chems. Yeah, they have the round 4, or whatever. They have the continuation, which has a couple other chems that they're hoping to get. Well, we'll see. We'll see which ones they actually get that aren't lattices. Nist does. And then there's also the South Korean PQ competition that has a bunch of other chems in their second round, which I mean to dig a little bit further on. So there might be others out in the world, but that's not relevant to this document. Okay, appropriate FIPS and special publications. Necessary information implementing chem in the FIPS 140 validated module. Yay! Securely combine key material provided quantum vulnerable with material provided by post-quantum methods. Yep. This recommendation does not discuss how or when to migrate from quantum vulnerable to establishment to post-quantum chems. Okay. This recommendation does not provide a specification for any particular chem. Yes, such specifications will be provided in other FIPS and specifically. This recommendation includes purely explanatory and educational material. This is extremely like, Nist said this, and they're like, this is guidance. This is not rules. This is not regulatory. Please, this is guidance. This is not a rule. Typically include material that pertains to what is approved. This SP special publication describes chems both generally and with respect to what is approved. Okay. I feel like that doesn't need to be, yeah, whatever. Specific requirements will be clearly noted with shall and must statements. If you're familiar with IETF language, these keywords, shall and must, are different in a Nist document. Shall is like the all caps must in an IETF document, and must is kind of like the should in all caps in an IETF document. And then their should. Yeah, their must is it's so bad because I mean like they're all just operating in completely separate domains. But yeah, the top level is that shall, bold but not capitalized, is the like Nist equivalent of IETF's must, all caps. So, and then the others are like, and it's kind of useful because their shall is the top one, and it's all about it's relative to will be tested by the module validation testing lab. So like this is the thing they'll actually check that you're compliant with by the module validation lab. Should is a strong recommendation but not a requirement, and then must is a requirement that might not be testable by your validator. So this is a thing that IETF doesn't have. Like they don't have any like compliance with a testing lab. Like you may provide test vectors in some sort of IETF document, but that's like completely maybe we won't. It's completely up to you. And like Nist stuff is like the source of truth is like what gets validated by FIPS 140 validation lab. Okay, terminology. Yeah, approved, FIPS approved, or Nist recommended. Yeah, specified, adopted, are specified in a list of Nist approved security functions. All right. Yeah, Kems ciphertext, not to be confused with public key encryption ciphertext or even non-public key encryption, just encryption ciphertext. There is a public key encryption ciphertext inside the Kem that is not public. And if you especially in MLChem, if you process over it, it depends on your Kem. If you process over it in a leaky way, like there were in some implementations of MLChem before validation, I think it was last summer, I'm not sure, or it might have been this summer, it's been a while. I think this was Kyber Slash. You can have a leak, you can have a mold, it's pretty cool. So not confusing your Kem ciphertext and a possible PKE ciphertext is important for security reasons, not just clarity reasons. Yeah, computationally bounded, lambda, cryptographically relevant quantum computer. Okay, this is going to become much more the term of art, terminology. Efficient algorithm. Yeah, encapsulation key. Exactly. Thank you. Yes. Exactly. Not a public key, not a private key, not a secret key, a encapsulation key and a decapsulation key. We love to see it. And the reason we love to see it is that there are a lot of public keys, private keys, secret keys in asymmetric cryptography. That's kind of the whole thing of asymmetric cryptography. Saying it's a public key or saying it's a private key or saying it's a secret key is not very useful to tell you what it does. For Kems, you have a key pair comprised of an encapsulation key, which is public, which you hand out and people can encapsulate to it. And then you use your decapsulation key, which is private and secret, to decapsulate those Kem ciphertexts. That's what it does. This is also why we would like to say that for a signing algorithm, we have signing keys and verifying keys or validating keys and so on and so forth. The one problem with this is things like Diffie-Hellman. Diffie-Hellman don't have a real good name for the public part and the private part, other than public share and private share or something like that. It's kind of tricky. But Diffie-Hellman's broken now because quantum computers, so haha, who cares? Hash function identifier. Oh, this is gonna come in handy. Key agreement. A key establishment procedure. Okay. Subclass. This is gonna be interesting because I didn't quite expect this to show up in this document. Procedure provides assurance to one party, then another party. This is the correction. All right, yeah, I can see that. Key confirmation provider. Yeah, okay. Key generation method, key generation key, encapsulation mechanism, key establishment, key agreement, Kem, and key transfers are types of key establishment. Yeah. Not my favorite. Keying material. Sure. Key pair, key transport, MAC. Family symmetric key criteria, input of data of arbitrary length. Yep, the tag, the output of MAC. Yeah. Authentication of the origin of the input data. Yes, I can. Must. Talk about that. Negligible. Yeah. Relative to the security factor lambda. Party. Yeah. Pseudo-random. Public channel. Yeah. Bullshit secret. Shared secret. Key. Sure. Strength, shall, should, side channel, symmetric key. Okay. Forming implementations of approved Kems are required to satisfy all the below testable for evaluation lab. Okay. Yeah. Okay. Few components of series transfers and appropriate. Okay. This is very generic. Except for random seeds and data. Can be easily computed from public information. All intermediate values in the Kem algorithm shall be destroyed. Yep. Before. Okay. Not when before, but before the terminates. Okay. Nonce is used in by the decapsulator. Nonces. Fuck. We hate nonces, don't we, folks? Don't mind me. I'm just posting. The reason I say gra is because like we could just not have nonces. We have authenticated encryption that doesn't require an exposure to nonces, that doesn't require us to say specific things about nonces, but I guess it's Nist, so they're gonna use GCM and a bunch of other shit that it's still kind of exposed, so alright, whatever. Multi-algorithm key sources in the shared secret shall be combined in approved key combiner. Oh boy! R5 is fun for images and can't control copies. Yeah. Alright, this is alright, we're gonna get this soon. This is relevant to my interests. Yeah. When requires the use of a Mac, it shall be an approved Mac route algorithm. HMAC, CMAC, or KMAC. KMAC's pretty nice. A little expensive, but shall compute Mac type with Mac key based on shit. Okay, alright. Yeah. CMVP will perform random input output test and attempt to certain values requirements specified during full functional. Not possible. Oh, cool. Alright, great. Awesome. Application of Kems parameters of the application of security strength must be selected. Okay. Alright, I'm going to skim through this because if you want to see more about Kems in general, you can see my read through on this channel of MLChem. Yeah, just test all the numbers. Like, how hard is it? Just like, yep. Yeah, over a public channel is a key establishment scheme. This is a key encapsulation mechanism. This is one kind of a key establishment scheme. Okay, security. Yep, this is our... I actually kind of like this diagram. Theoretical security. Selecting a chem that is a collection of mathematical functions is well-defined, correct, and satisfies an application-appropriate mathematical notion of security. Oh, ensuring the security hold in practice is a complex task. It relies on 3 conditions. Only 3? Theoretical security, implementation security, implementing the selected chem real-world algorithm in a secure manner. Yep, and deployment security, deploying the chem in this manner is secure the relevant application using the shared secret in a secure manner. Yeah, I generally agree. Sure. Should these conditions security chem is theoretically secure is implement side channel countermeasures so it does not without side channel countermeasures. Whereas deployment devices physical vulnerabilities is likely to be secure in practice. I agree. History. Yep. Chemdem. Blah, blah, blah. One new standard. More likely to follow. Ah. Okay. Ooh. Alright. Oh boy. They're bringing the Greek symbols. Okay. A chem, denoted by pi. That's pi, right? Capital uppercase pi. This is a very kind of surprised that they're doing it like this. They didn't do it like this in FIPS 203. Yeah, that's just pi. They didn't do it like this. I kind of liked it the other way better. I'm comfortable with this, but if you're not a fucking crypto nerd, this might be a little bit foreign or kind of scary. Anyway, it's a whole scheme and it has sub routines. It has, component functions. Param sets, a collection of parameter sets. That's dumb. I think we should redo that. Keygen, probabilistic. Oh my god. Do you want to show the puppy? Guys, there's a puppy. Hold your horses. I think I have 7.
This is Lily, short for Lilith, primordial she-demon. She's 10.
She's settling in. She doesn't know anything about cryptography yet. I'll teach her. Alright. Probabilistic. Produces, yeah. Parameter set as an input. Yeah, sure. Produces or is a generic thing. Yet. Produces an encapsulation key, EK, and a decapsulation key, DK, as output. Encaps takes a plain text, a parameter set, an encapsulation key. That's true. The plain text is the random crap generated inside. Yeah. And decaps takes that chem ciphertext, deterministic, accept a parameter set, a decaps key, the ciphertext. The chem ciphertext is input and produces a shared secret. K prime is output. Okay. This section views Kems as purely mathematical objects. Labels P, E, K, D, K, C, and uppercase K and uppercase K prime are viewed as abstract variables that represent, for example, numbers or bit strings, and implementations representative of concrete data types. Cool. Yes, definition 1 only requires basic properties for components to make up a chem. Needs to be useful and secure. I like that. Useful. A chem should fulfill a number of additional properties. Properties correctness. Shows that in the ideal setting, process in figure 1 almost always produces seems to save both parties. Definition experiment for correctness. Nice. Yep. It should, is correct if for all P in the possible parameter sets, correctness experiment for P results in K equals K prime with all but negligible probability. Indeed. When keygen and caps are invoked in the correctness experiment, is implied that the randomness is generated internally and uniformly at random. If one wishes to explicitly refer the randomness used by the algorithms, yeah, the expressions can be used. I don't know. If I were authoring this document, I wouldn't do this. But yeah, if you're modeling it, if you're doing shit, you're trying to model it, you kind of have to have your randomness explicit in the thing. Oh, what a good girl. Sorry, I'm distracted by a puppy and another corgi. Good boy. Yeah, it is, but in FIPS 203 for ML Chem, they don't do this. And I mean, I'll keep reading, but maybe they're doing this because they've had feedback that they're like, well, how do I model this? And it's kind of left up to, an academic reader. I don't know. But they're good dogs. Sorry, chat. My dogs are over there. Especially if this next section is sufficiently self-contained, it's probably fine. All right, let's see. Yeah, explicitly return to the randomness R. It's explicitly kind of an input to keygen. And actually, now that I think about it, this is kind of nice because when you're trying to, because ML Chem, the external surface area of a ML Chem implementation that's in a module has, you have keygen, ncaps, decaps. And keygen and ncaps are probabilistic, and they source randomness within the externally facing functions, keygen and ncaps. And then internally in the spec, they specify keygen _ internal and ncaps _ internal and decaps _ internal. But keygen internal and ncaps internal are handed randomness that you've sourced. So I think they're kind of learning some stuff from when they did FIPS 203. So they're exposing it a little bit because it's not just relevant to modeling, but it is kind of relevant to testable implementations and reproducible implementations. So I'm gonna keep going. Okay. Wait, why did they change R to S? I guess they're different. Whatever. Okay, just R1, R2, R sub 2, whatever. These expressions can serve the process of re-expanding a key pair by running keygen and the stored teeth R. Oh, sweet. How good of them to explicitly say that sort of thing. That's very good for stuff and things. Too simple and instructive examples show object chems that satisfy definition to abstract. Yeah, two not used. All right, I'm gonna fast forward through some of this. Key transfer using PKE. Yeah. Maybe you should also say do not use. I just want to rename that. Don't use this either. Just for reasons. Efficiency, correctness, and security properties come from PK. I mean, yeah, don't do that. Don't do that. We have all these chem constructions where we don't do this for reasons, especially binding property reasons. All right, 6.1 discusses 3 additional examples of chems, each of which is an improved algorithm, ECGH chem based on, that sounds like DH chem from the IETF HPKE document, which is fine. RSA, SVE chem, RSA key transport, ML chem is the lattice-based post-quantum chem. ECGH chem and RSA's SVE chem based on Nist standardization key styles just confused as chems. ML chem is the first key establishment scheme to be standardized by Nist directly as a chem. Okay. I feel like that needs to be rewritten. The markup key transport key agreement. Key agreement and key transport. Key agreement. Yeah, wait, hold on. Yeah, like this little example. Randomness. Key ciphertext encrypt, basically encryption randomness. But this I don't like it. This is not the output is not directly, it's not bound to the ciphertext, and it's not bound to it all depends on the properties of the public key encryption scheme. If this is shit, everything's shit, and we have designs for Kems that account for that. So 480. Yeah, fair enough. I can just see somebody getting some bad ideas just from this. Even though it says like 2 lines above, like, don't. Like, I feel like this is almost unnecessary, but I don't know. It also doesn't like, I don't know. I don't love it. Reminds me of key agreement and key transport. Key agreement, Diffie-Hellman. Parties contribute information influences file share secret key. Yep, and key transport. Yeah, this is another thing. This, arguably, if you do it with the FO transform style, you can basically argue an FO transform Kem is much closer to key agreement, because no matter the properties of the underlying PKE scheme, you can just like shove everything into a KDF, the ciphertext, the encapsulation key, whatever, all the public information, and some private information, and it will all depend on the contributory behavior, different than a Diffie-Hellman context, but still like both parties have influence on the final shared secret that comes out. With this design, it completely depends, not just it just completely depends on the properties of PKE, whereas you can have Kems where it doesn't matter, it only barely matters on some of the properties of PKE. You can just shove a whole bunch of shit into your internal KDF and you will have something that's closer to key agreement, no matter what the properties of the underlying PKE. Anyway. Both parties contribute information. Key transport, when party selects the key and then transmits in some form. Yes, agreed. Depending on the internal structure of encapsulation function, a Kem could be viewed as either key agreement, yes, or key transport scheme. Yes, exactly. Very good, Nist. Shared secret key and normal Kem is a function of both the randomness provided by Bob and the randomly generating encapsulation key of Alice. Therefore, MLChem can be viewed as a key agreement scheme. I agree. As an example, Kem for PK shows the encapsulation operation, and Kem might simply consist of Bob generation of a secret and then encrypting it. This is precisely key transport. Yes. Okay, fine. It's illustrative. Probably want more language about not using it in practice. If the application requires a particular type of key establishment, either key agreement or key transport, this can be achieved by using any Kem by taking appropriate steps using standards metric key controls. Okay, theoretical. Semantic security, yes. But uniformly produces shared secret key that is uniformly random and unknown to adversaries. Properties should hold despite the fact that adversaries can freely observe the messages transmitted by Alice and Bob. In case of Kems, encapsulation key and ciphertext should reveal no information about the underlying shared secret key K or the encapsulation key TK. Moreover, even adversaries who somehow learn partial information, like the first half of K is accidentally leaked, should not be able to combine that information with the EK and C to learn more, e.g. the last bit of K. Informal notion of security can be rigorously formalized. Yeah, semantic security. Passive adversaries and chosen plaintext attacks. I love security game definitions. Now that I understand them, I love them. Yep. The adversary's goal is to distinguish encapsulation key, a ciphertext with a true and either the true shared secret key, underlying C, or a freshly generated random string. Yep. So basically, the adversary is basically able to say like, hey, decrypt this, encrypt this, and he has to be able to distinguish between what you actually gave him, as opposed to a chosen ciphertext attack. That's a terrible way to describe it, but yeah. Unextinguishable ciphertext or is in CPA if for every quickly A probability that A wins an experiment is now usually close to 1/2. Yeah, so you do it in caps. Adversary picks a bit and another bit, sends, yeah. Oh, the challenger to the adversary. This is a different formulation. I hate this. Yeah, given an EK, a ciphertext, and a key, send it to the adversary. They have to distinguish, and they have to say if it's a random one, which one is it? Chosen ciphertext attack is very, like, it was the Kems specific version of chosen ciphertext attack security was the security thing for Kems, that the whole Nist PQ competition about Kems was like predicated upon, basically. So I usually talk a lot about binding properties. They weren't a thing. They weren't a formalized thing at all during the Nist competition. So they came much after. So like the big kahuna of like what kind of security properties does a Chem give you is chosen ciphertext attack security. Real experience in case there was and sometimes actively interfere with key establishment processes and use the ability to uncover the shared secret key. Active adversary convince a colonist user to encapsulate some ciphertext of the adversary is choosing. Yep. Natural ask whether other ciphertexts are still protected. In CPA security is insufficient. One must consider a chosen ciphertext attack. This is the experiment. So a challenger has honestly generated keys, honestly generates some ciphertext, generates a random key, shared secret key that's different, and a random bit, sends the encapsulation key, ciphertext, and the randomly chosen key. These game notation could be improved, in my opinion. Choose a random one. Choose either the real one or a randomly sampled one. Hand it to the adversary. Adversary has access to a decryption oracle via the decapsulation key, and they have to be able to guess which one it is. Is it the real one or whatever? And so this is the challenger being able to hand you a random ciphertext, and can you deduce anything based on the random ciphertext? And if you can't, cool, then it's indistinguishable under chosen ciphertext attack. Similar to NCPA experiment, the adversary is now granted black box oracle access to the encapsulation function. Adversary is allowed to submit ciphertext. That they generate and get the response of decaps. Only restriction, they cannot submit the actual ciphertext C produced by the challengers, since that would make the game trivial to win. Yeah. Yep, and the advantage is negligibly close to 1/2. MLChem, the first post-quantum chem necessarily has been believed to satisfy NCCA security. Yes, definitely it is. Although the NCCA proof for an FO transform like MLChem is apparently kind of gnarly, especially if you're formalizing it with something like EasyCrypt or whatever. I still don't fully understand why it's so gnarly, but someone maybe can explain it to me. But I will probably have to stare it straight in the face soon. And I think it's like a multi-phase game transform thingy. Maybe there's state management involved. I don't know. Okay, I'm gonna zoom. This is kind of just like secure cryptography implementation stuff. Approved chems implementing according to standards. In particular, concrete data types will be specified parameter sets, key cyphers, and zero secret keys. Yay! Oh, they're looking chem. Yay! I like that. Approved elements. Yeah, random bit generators and hash functions. This is a little bit annoying because, like, if you want to do an implementation like I have that's theoretically FIPS compliant and not like skewing, you have to use one of their RBGs. You can't just use like, I don't know, like I write a lot of Rust, so I would like bring in the rand crate and I'd just be like, get random from rand, and it uses whatever it has under the hood on whatever system you've compiled to. And they're good. They're usually good. But if you want to theoretically be FIPS compatible, you have to make sure that the random number generator underneath that is an approved FIPS DRBG. Yeah, right? Like, maybe. Rand : FIPS as a module would be handy. I'm not using one. I'm using a separate one that was like a separate crate that's specifically one of these DRBGs or whatever. But what are you gonna do? If you care about FIPS, you care about that shit. If you don't care about FIPS, you don't have to worry about that shit. So you could implement MLChem with just, rand, get random, but it will never be FIPSable. It will be FIPS, except for the fact they use a separate random number generator because. Testing validation, yeah, blah, 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 blah. Nist implementations must correctly, not IETF must correctly implement mathematical functionality target. Yeah. So validation tests only test input-output behavior. Implementations need not follow the exact step-by-step algorithmic specifications in the standard by specifying the relevant chem. And the implementation that produces the correct output for every input will pass validation. Yes. I have a feeling this is part of the reason why you might have FIPS validated code that's fine. But if you want to formally verify or model or any of that shit, you might want to stay kind of close to the specification. Just saying. It is the standard. And yeah, you can be in here, in, FIPS 203, it says do it in this way. We do it in the mathematically equivalent way, which is allowed under FIPS. We do this instead. I've seen that. And sure. But you have to comment your code and document it very well to make sure that that's clear what you're doing. I'm moving some windows around. Okay. Go checking. Yeah. I'm gonna zoom through this. Destroy your intermediate values. Yes, please. Okay. Establish a key with a gem. Highly flexible. Are they though? Not like Diffie-Hellman. I don't know when we're gonna get away from Alice and Bob. Yes. Choose your parameters. Do the thing. I feel like this is a little bit redundant. Use the shared secret. If the appropriate conditions are satisfied, this coming out of section 5 and KA will equal KB and can be used for any symmetric key. Yeah. This is something that Nist has made very clear, is that you can spit something out the back of MLChem and just start using it. You can just use that raw as your AES GCM key or whatever you want to use it for. Most protocols will not do that, like TLS read won't do that. I think SSH will not do that. Signal definitely does not do that. iMessage does not do that now. Almost every protocol will not do that for security protocol reasons. You kind of want to separate all these things. You want kind of key separation and domain separation, and especially when I meant to write a blog post about this. I haven't finished yet. If you're modeling the thing in the formal realm of cryptography, this can give you nice oracle cloning sort of stuff, as opposed to having a single oracle of a hash function or a KDF or a PRF or whatever you're using. You generally just want to separate. FIPS does not require you to. So there's that. I think that's okay. It's okay that the thing that comes out the back of MLChem is secure enough in general, as just a cryptographic secret that you shoot out the back. It's secure enough to use it that way. That's great. It's not really about the MLChem part at that point. It's about the rest of the protocol and the rest of the stuff that you're doing with that shared secret that comes out the SN of MLChem. Definitely improvement over ECGH. Yeah. I think they wanted it that way. I don't remember if they said that in their calls, but I thought there was a concatenation happening here. Yeah, so this is one of the kind of annoying parts just for Photon resilience. Absolutely. One of the things that they had, in the design of Kyber that evolved into MLChem, one of the the what was it? Implicit rejection, FO transforms. MOChem was one of them. The Kyber was one of them. There are others. There's also explicit rejection, which is basically like if you were handed a Kems ciphertext and you tried to decrypt it and decapsulate to it, and then you tried to recompute what you did to make sure that, you know, you're resilient to a chosen ciphertext attack, and you failed, you computed the wrong thing that you weren't supposed to compute, it didn't match, you can explicitly fail, which is literally throw an error of some sort, like return null or return an error. If you're panic, you know, you probably wouldn't want to panic, but you return some sort of error. You return some sort of signal that said this computation failed, which can have signals. And if the way you encode that is saying like, if I return all zeros, that means that this failed. You cannot use that as a shared secret key. Like, that means it's like if you can always trigger a decapsulation failure, then you will always have the same value as a shared secret, and whoopsie doodle, everyone can just listen to all the traffic and decrypt all the traffic that's encrypted under that shared secret, or something that's derived from that shared secret in a deterministic way. That's why things like Kyber and MOChem and others that use a similar thing use a implicit rejection FO transform. Ostensibly, that's why. So that in the implicit rejection way, if there's a decapsulation failure, there's an alternative cryptographically strong rejection value that's returned of the sufficient bit length and all that stuff. But it will be different than the quote real shared secret if everything went perfectly fine. Read Sophie Schmig's papers about the name's blanking on me at the moment, about how the implicit rejection flows can lead to different binding properties. So that's interesting. But yeah, that was a design property that probably will have good foot gun resilience of just literally just like taking the key that shot out the back of MLChem, whether there was a decapsulation failure, everything went right. That is still a cryptographically random, pretty cryptographically strong value that you can start encrypting stuff with and not die, and not spit out all zeros and just accidentally everyone agrees that the shared secret is all zeros, and then you have just like a surveillance backdoor or whatever it is. So there's that. All right, static versus ephemeral. Key confirmation. Yeah, post-processing key confirmation steps. I feel like some of this is built into Kems internally. Okay. Conditions. Yeah. This is just sort of like using Nist cryptography securely. Oh, puppy. Huh? Certain key establishes keys. Blah, blah, blah. Kems on the yeah. Foreign key charge. Yeah, the transfer of the shared secret to shared secret key. Yep. Yeah. Kems on the other hand, by definition, outputs a key that's ready to use. As a result, key derivation is not required in using Kems. I'm going to talk to some people about this. Protocol people. Still some applications using Kems will require key derivation. Yep, like a whole bunch of them. This is the case. For example, in Kyber, in MLChem, SHA-3 is used as the KDF, basically, inside the PRF. And this is Nist approved. Sweet. There's no label inside to domain separate any other use of SHA-3. What are you woofing? Hey, go on. Went a long way around. Yeah, for example, do you know what G is? G is, wait, come back. Yeah, G is just SHA-3. So when you invoke SHA-3 here, this is outputting the shared secret here and the randomness, but you can do the deterministic randomness. This is the random message. This is just random number, and this is a hash of the encapsulation key. And then that's it. So if you want to, if you're using SHA-3 like hybrid, you might want to domain separate stuff. Domain separating something internally versus externally is like kind of tough to argue about. If you care about it, having this say like, oh, you don't need to do anything about this key when we've stuffed it out, I'm like, if they had written this such that G is defined as like SHA-3 with like a label in the front that's like ASCII encoded bytes, MLChem 512, MLChem 758, MLChem 1024, I would be much happier. They probably have some arguments about why they don't think that's necessary. They don't want to do that. But like, I'm thinking at the protocol level. Do they though? Because G, okay, hold on. Well, they do for their usages, for key derivation versus, yes, for their usages, they have key derivation and then they have the KDF internal to actual outputting the shared secret. But across the SHA-3 that's used for spitting out the shared secret out of encapsulate and decapsulate versus, say, using SHA-3 in X-Wing, because we invoke MLChem, which has SHA-3, and we do X25519, and then we do more SHA-3, but we domain separate our SHA-3 at the X-Wing level, and they don't. So, but yes, they, for all their hash function usages, they're using separate hash functions. They're using shake, they're using SHA-3, and I think there's one more. Yeah, shake 256. They're using shake 256, shake 128 for different usages, which is fine because of the nice, sponge constructions. It's approved by Nist to do that. Yeah, they did a good thing in their own little box, which is completely understandable. But I kind of wish that they... And then it's arguable, like, well, how do you do domain separation across domains when you don't really know all the domains? You're just sort of like throwing some shit in front of in the front of a pre-image input to SHA-3, and so like I can understand that it's hard to like really make the argument that you're doing something useful there, but I don't love their sort of like, you can just take this thing out the ass of SHA-3, MLChem or another chem and just use it raw for any of the ones that NIST has approved. Like, it's not going to output all zeros, but I wouldn't do that in my protocol. I would do something else to that shared secret and put it through a KDF or some other PRF with some sort of domain separator when I invoke it. So, here we go. Key derivation consists of applying a key derivation method. KDM, I don't love it. Just call it a KDF. Everyone else calls it a KDF. All right, for transferring a given key derivation key and some other data, possibly some other data, keying material a list of keys. An example is concatenate the key derivation key with optional data Z, apply the KDF. Ha ha. Ha 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 ha. Ha ha ha. Okay, fine. Method. A KDF is a type of method. Whatever. Final output is simply KDF function with the preimage K concatenated with Z. Yes, SP856C. Yeah. Key derivation for chem pi is needed. Shared secret output by pi. From encapsulated cast, I use a key derivation key supplied to an approved key derivation method. Yep. Including SHA-3. In case where KDM is 56C, use shared secret account data input to KDM place the shared secret. Okay. Yeah. Key confirmation. Do I see something very concrete? For example, bilateral key confirmation is provided during TLS handshake with TLS 1 Yeah, sure that does. Sure it does. Oh boy. Hey, look at that. It's got a label. You like labels here, and not with your Kems. ID, yeah, 6 byte character string that the MAC data is used for. Okay, 4 valid options are KC1, KC2, KC1. All right, yeah. Identifiers they use to label, and the ephemeral data, and then extra shit. When a nonce is used, needs to be provided and encapsulated before they can complete. Okay. Optional data. Yeah. Obtaining the key. Interesting. After computing plain text secret value, find key generation method, blah, 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 blah. Alright, execution of this license, just 2 parts, combination key. Got it, and the data key. Okay. When generation is not used, key combination for versus the plain text of the outcast. Case key and data key. Oh. What? This could be improved. If I'm just scanning this, it looks almost exactly the same. Just one of yeah, whatever. Okay. Yeah. All right. So we encapsulate. Yep. All right. Okay. Yeah. Just put a label in front. We'll do it there. Why won't you say? Yeah. I don't know about that. Construct MAC data. You MAC using the first part over the whole thingy laid out up here. Yeah, that thingy. And then that's the tag, and you send all that shit. Where's the tag? You send the tag and your ID and then the extra shit. All right. Construct MAC data, and you do the MAC verification. Spat out from the KDF over the chem key, chemistry secret. You verify against that thing. Abort. All right. Oh boy. All right, I'm gonna go through this quick, and then I'm gonna peace out. Hybrids, blah, blah. I hate this. Who needed this? I guess fucking hybrid is the most Is hybrid the most overloaded term in cryptography? Maybe. Someone might have another one. Yeah, it makes sense. Multi-algorithm key establishment scheme. Makes. I don't hate it. It's better than hybrid. Enter secrets generated using 2 or more key establishment schemes. You call it components. Yes, several schemes. Not necessarily the multi-algorithm scheme has the same interface as its components. Correct. I've made several of them. In this document, for example, multi-algorithm schemes will always be Kems, other components need not be. Yep. Okay. Yep. Scheme will be secure if at least one of the component schemes is secure, whatever that means. Parenthesis, whatever that means. May provide some protection against vulnerabilities that are discovered in one or more component schemes after deployment. The migration to post-quantum blah, 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 might initially include... God, the fact that they're saying this is just going to be like, Nist likes hybrid. Nist is totally cool, which is true. Nist is okay in principle with hybrid. NSA for national security systems says it doesn't want hybrid, which I also understand. But where is it? There it is. X-Wing mention. Take a shot. See, okay. Whatever. I need to wrap this up, but sometimes referred as hybrid key establishment. Swing is a hybrid post-quantum traditional chem built from 2 components, MOChem and extra 5.19. Okay. Approved approaches for oh god, all right. Establish shared secrets. 2 stages. Yes. Combined shared secrets. Yes. I hate key combiner. I know this is a term that came from a paper, and the paper is very good. I much prefer something like FO transform, but that's a very, I don't know. I just don't like, what combiner do you use? I'm like it, the components, the parameters, and the techniques to combine them all matter so much that being like, what combiner is a bit like, I don't care about a combiner, I care about the whole thing, to actually analyze it. Okay, section 552. Okay. Velocity, it's actually a single temperature component Kems. Oh, okay. Yep. DC chem. Yep. DH chem. More of a hybrid PQC adaptation. That's basically what X-Wing does. It takes DHChem laid out in the HPKE RFC, and instead of doing 2 rounds of KDF, it's putting the whole static and the ephemeral Diffie-Hellmans of it, putting them all in line, concatenating with the shared secret from DHChem, extra 5009 DHChem, and just the X-Wing. Sorry, Chem. I can't remember my own fucking thing. It's terrible. I should have known better. Yeah. ML Chem shared secret. X-Wing shared X250 shared secret. X-Wing ephemeral public key. The ciphertext. X25519 static encapsulation key. Static public key. And then the X-Wing label at the end. Through SHA-256. This is the X-Wing label. Everyone has opinions. But in the HPKE document, like, all of this is also put through a KDF, like HKDF, for example, I think is one of the options that they specify. But we're kind of smushing it all together and putting it through. It's kind of, if you kind of squint at it, nah, I'm not going to make that comparison, but that's the idea. I wonder if what they're doing here is not that. They're doing like DHChem through a KDF, taking that. MLChem, which has its own KDF, which is SHA-3, taking that, doing another KDF. We'll see. Easily adapted, combining more than 2. Yeah. I know some people want to do that. Mining chems with long chems, yeah. Okay. Parameter sets for both of them. Eco miner. Pair of shared secret keys. Yeah. Pair of ciphertext. Or a seed. Use a seed to generate both if you can, which you can do with MLChem, which we do in X-Wing. You should do like we do in X-Wing. It's good for you. It's good for security. Output shared secret key. And the parameter closet. Form. Yeah, I know. I know they have to do it this way to make it super generic. Yep. P, yeah, parameter. Yeah. CM. That since the info to key combine include the composite encapsulation key, the decapsulating party must retain a copy of that key or maintain the ability to recreate it. Very good. Because that means seed after performing key generation. Yep. Extending the obvious way to composite instructions. Extending to case completely general knowledge. Yeah, multi cells can be more complex as components and can. Yes, they can. Like some of the things can be easily seedable, some of them are not. Some of, like, if you're doing like Diffie-Hellman based things, like you have to do kind of like 2 keygen, well, 1 keygen for static, and then you do other shit for the actual encapsulation. You're doing keygen again, depending. It's not. The kind of complexity can kind of become fractal at some point. And some people are like, ooh, you just do it again. It's like, yeah, but like at the protocol level, if you look at the thing as a protocol and like using it, it just like, and negotiate, like it just, meh. Yeah. All right, I gotta wrap up. Oh, okay. I'm gonna go. All right, approved combiners. P800, blah, blah, blah. In brief, okay. Yep. Yeah, it's just do the same thing. Oh god. It's just KDF with some other shit, which we kind of did, the 2-step. Cool. Oh boy. How does this work with SHA-3? Yeah, bork. Oh, this is curious. Okay. Probably looked at this 5 million times. When it's the SP800 series, all the numbers just kind of run together. Okay. This means the quantity Z can be the shared secret of MLChem. No dur. I actually kind of like this. If this is very similar to the split PRF construction that iMessage used to do their post-quantum update, PQ3. I think it looks like it. Someone can correct me, but I think they used HKDF for it. Cool. All right. Yep. That's funny. Both one-step, two-step derivation, 856 CR3. Shared secret to have the form concated. Pardon me. Yes, CSL key combiner, KDM S1 concat S2, and some other input for a 2 algorithm key establishment scheme. So all this other input stuff, quote, matches X-Wing by putting both of these, this kind of matches explicitly X-Wing, this kind of implicitly matches X-Wing. This one. Putting your ciphertext and your encapsulation keys in there, which X-Wing doesn't totally do. It does it for the DH side, but there are other chem combiners where if you just like put in your full encapsulation key and put in your full ciphertext, you get like maximum binding, and it's really nice. Modulo key generation and key management. Yeah, I think you're right, Strode. Okay, two-step method, and then yep, simple. Yeah, this is good. I like this. You're damn. You're in the snow. Wait. Oh, this is the new camera. It is a DAC. This same lighting didn't used to look this DAC. This is a fancy Sony thing, and I don't know how to configure it for shit. I am done with cameras. So maybe it'll look better soon. I don't know, but it looks wicked DAC for now. We'll see if anyone else shows up in the middle, and then I need to plow through this for myself, finish this, and I'll talk a little bit about the vulnerable protocol when you use a chem that uses weak binding properties that they specifically cited. I'm going to go back a little bit. So I left off somewhere in here, I think, somewhere past here. I think I skimmed through this. And sort of like read through this and was like, yeah, this is boring. Yeah, and this is the like authentication. Fast forward, yeah. This is sort of like the quote mutually authenticated version. It's not quite. It's just sort of people agree on the same thing. That's mostly controlled by the parameters of the chem that you use. I want to go back and basically go over some stuff that I already went over that I didn't care that much about until Cost Kramers read this and sent mail to the PQC forum list, which was managed by Nist and run by Nist. And this is where they had announced the draft of this document, to be like, you've specifically told us about a protocol in a different Nist document, SP, whatever it is, I think it's SP. You referenced 3 of them. One that was based on Diffie-Hellman, one that was based on RSA, and one that was MLChem, I think. MLChem was FIPS 203, it's brand new. The other 2 are not brand new. And NIST basically said, oh, here's a figure 4 that I kind of skimmed past. Figure 4 is a protocol you can do, and I think figure 5 is the authenticated protocol. You can use these traditional chems based on RSA in here, and that is one example. Yeah, this guy. Yep, they are approved algorithms, all right? And basically, Cost Kramers is basically, if you use this RSA SBE chem, it's basically a ability to establish a shared secret using RSA encryption, which is like based, like they literally have the functions in the scheme. They just say literally use the keygen function for the chem equivalent keygen function, use this other function for encapsulation, and then use this third function. It's called this other thing, but you can use it for decapsulation. And it's like effectively a chem, and it is a chem, but just sneezed off my headphones. It's not a very good chem, and when you use RSA SVE in figure 4, and I think figure 5, you do not actually come to a shared secret, agree on a shared secret that is bound to the public key, the encapsulation key that you think the person that you are trying to actually encapsulate to, because an adversary can get in the middle, and Eve can basically manipulate the meddler in the middle, or Eve's in the middle can meddle and say, ooh, I'm gonna present a different key and have Alice encapsulate to that, and I can present something else to Bob, and Bob can encapsulate to that, and they think that they are agreeing on a shared secret between Alice and Bob, but they're not. It's Alice with Eve and Eve with Bob, and they can manipulate it in that way. And this is like a classic error. I'm just going to pull it up to make sure I'm not misrepresenting the whole attack. It's basically, I think it's an unknown key share attack. Yeah. Why not logged out here? Right? No? That's a long thread. Okay. That. But first I'm going to go through the specific algorithm. And TLDR, this is just very unfortunate because the example RSA SV is a official Nist traditional, not post-quantum chem, and they're specifically citing it as like a traditional chem and a protocol, a back and forth protocol, how to do a key establishment, both unauthenticated and sort of, checking that, everything is kind of mutually authenticated with over the shared secret. But literally one of the examples they give of using this primitive in that thing is insecure, and it uses and has a vulnerability in it, and it's a pain in the ass. The DH chem that they also cite, that's in another Nist document, does not have this problem. This is why I got through the protocol, but I didn't get to here, which is very funny. So I'll go linearly and like continue to go past the hybrid shit, and then I'll get to that. So the DH chem that they cite, it's a slightly different variant of like the DH chem that's specified in HPKE, which is from the IATF, which might be in broader use. They're not exactly non-interoperable, but they're definitely broadly interoperable. Like HPKE DHChem is quite specified, and the other thing in this Nist document is not as well specified. There's a lot of room to include things or not include things, and that actually changes to like what you agree on and whether the hashing is separated or anything like that. And so it has different binding properties, but it's less a matter of like the binding properties, which are okay because it's Diffie-Hellman. And I think there's been recent analysis to confirm this. I think that's in Klaus-Kramer's paper, Keeping Up with the Chems, like the 7th, 8th, 9th version of it that's on ePrint. But it's mostly a question of interoperability. Anyway, we don't really care about that. We care about the RSA chem they cited. So I'm gonna skim. Yeah, this is figure 4. Yeah, this is just literally how to do key establishment using a chem in just like a generic protocol. So you decide on which scheme you're using, you decide on the parameters you're using. Alice generates a key pair, spits out the key pair, sends her public encapsulation key to Bob. Bob uses that, encapsulates to Alice's key and spits out the shared secret and the ciphertext. Sends the ciphertext over to Alice. She decapsulates the ciphertext using her decapsulation key and also spits out the shared secret. So shared secret, shared secret. If you have followed me at all, you know that binding properties are a thing for Kems. And I wrote a blog post. It's linked to my blog. It's the only blog post that's on my blog at the moment. I have a couple more drafts in flight, but I'm terrible at writing blog posts. If you see me anywhere else. This protocol is very simple, but the simplicity also means that almost the entirety of this protocol and like what you get, what this shared secret like gives you is almost entirely dependent on the properties of the scheme, the Kem itself, pi. The binding properties, if it's this thing won't let it be used unless it's in CCA, so there's that. But literally, if this is like classic make-a-lease, there's like I would not recommend to be used in this protocol. Like we have to do a bunch of more shit because basically it's spitting out the raw shared secret and not doing anything else with it. So if you were proposing that we use this protocol in production or something like that, even before you get to the binding property shit, you would basically be like, well, don't we want to do session independence so that we would, meaning if everything, like we ran it exactly the same, yeah, there's keygen, but there's also a possibility that like, say you seeded your RNG shittily so that you spat out the secret key, you sourced more randomness, and it's all replayed exactly the same. Say you like seeded your keygen, your RNG on your system from like, the start of the epoch or whatever. So you're just literally like, whatever. If you rerun this and you have all the same values, you come out to the same exact, that's actually not a really good example. But anyway, what you would want to do is when you want to put all your public values into the KDF, the key derivation function at the end of the handshake of this protocol. So this is, maybe you put your parameters, the start of the thing into your protocol. That's not a bad idea. And kind of do that in TLS 1.3, for example, because when you're doing the handshake, you're establishing like what elliptic curves you might be using, what, extensions you might be using, what signatures you might be using, because you have to offer them. And the other side has to say whether they support them or not, or like start negotiating using them or whatever. So you've got parameters, you've got your encapsulation key. You would stick that into your KDF like as an input to a function. You would concatenate that in or do it in rounds, the way TLS 1.3 does it. And you would put this ciphertext here, the one that Bob generated. And then you would also concatenate, of course, the shared secret. And then you would probably, like, if you're doing it in rounds, sort of like you do one layer and you put the output of that into the inputs of the next thing and you chain and you chain and you chain. This is seen in a bunch of different protocols. And in each layer, you would probably put a label as part of the input of the thing that you're hashing or putting through a KDF function. So like you would put like something into a KDF function, it would be like parameters concatenated in like some sort of like ASCII encoded thing. And you put the parameters or the flag that represents the parameter. And then the next layer would be, encoded label, encapsulation key. And then you have the actual value of the encapsulation key and you put that input in and you chain that. And then similar with the ciphertext, and you try to chain that as well with the previous outputs of the previous things. And then finally, you have the shared secret key, and then the actual shared secret key value, and then the thing that's you're chaining before. Or you concatenate all these things. I know, Chris. Absolutely. So, the fact that this is like just like raw dogging a protocol, key establishment is just like, if I were reviewing this, I have all these notes. So anyway, before you get to the binding properties of this Kem, that's stuff that you would probably want to do anyway, because it binds to the public values that you are establishing this thing over, so that if someone offers you a different encapsulation key, then you're absolutely coming to agree on a different shared secret for this session. And then if you're using that the final shared secret that comes out of the KDF, at the very end, so that if you're doing your, symmetrically encrypted data over this key, it's going to be different than the one offered by, even Alice, who generated an ephemeral key pair in a different session. Because that saves you from negotiating the same exact key that this protocol would have you come out here. If, for example, this protocol, this Kem protocol pi, is kind of shit. Some of these chems are kind of shit for reasons, and like they'll spit out the same value. There's some cases with Michaelis, but it's mostly about this kind of session independence thing. You want to do this anyway, but this one doesn't. It's just spitting out the raw shared secret, and like MOChem came out of the Nist competition with like this implicit rejection FO transform. So it means that if you didn't come to an agreement, if like the Kem decaps didn't work, you'll come out with a cryptographically long, sufficiently robust, with enough entropy random value. It's not like you're going to spit out 0 or something like that, and everyone ends up agreeing on 0, and it's very breakable. There is that, but it can come out with the same value if you're decapsulating to, with the cipher, I have to go double check. It can fall back, but it's using it raw. It's not binding to the encapsulation key. It's not binding to the ciphertext, and it's not maybe internally. It depends all on the details of the Kem itself, all these details, and that includes the binding. We don't know if the shared secret that's spat out raw and used raw from this key establishment says anything about the encapsulation key that we used to encapsulate to it, or the ciphertext that Bob hands to Alice, or any of that. It's all about the specifics of the Kem here. You can, as a protocol person or a protocol designer or a protocol, doer, can mitigate that by including the, all the public data and the public parameters and all that sort of stuff into your key derivation schedule. You can mitigate a lot of that stuff. It's good protocol practice. It gives you nice protocol security properties to do it anyway. But it's yet another, if you're going to have different chems or you don't understand the properties of the chems, it also mitigates the chems like being like, whoopsie doodle, like this doesn't actually bind to the like encapsulation key. I think that's the thing with MOChem. If the FO transform fails, come back. No, never mind. There it is. If the decapsulation fails because of the FO transform, it's completely attacker controlled. The value that's spat out is completely attacker controlled, which is a good idea when decapsulation is failing. You don't want to leak anything to the attacker that is leaking information. So I'm trying to remember. Yeah, so we decrypt, we have message, and then we do another hash function. We put the message we decrypted out and the hash of the encryption key, the decaps key, and then we check that. This is the value we prepare, and then we re-encrypt to see if the value that we get is the same as the value we were passed, and if we don't, we return this other thing. And yeah, it's completely it's controlled by the ciphertext, which can be high entropy, and the implicit rejection seed or randomness that's encoded in the decapsulation key, and is never used for anything except for this explicit purpose. So it's not entirely attacker controlled. It's controlled by secret data that the key holder only knows and only uses when they're decapsulating, but it's also tightly controlled by the ciphertext. And then if on the corollary, if everything is working well, the actual key that you use when decapsulation doesn't fail is dependent on the plain text message randomness seed that you encrypted with the public key encryption, and the hash of the encapsulation key, the public key. So what this tells us is MLChem, by design, tightly binds the public key as long as you have a secure hash function. This is actually encoded into the serialization. It's encoded into the encapsulation key. You can completely rederive all of this from the seed format, so you don't have to hold the hash of the encapsulation key around all the time if you have the seed for the key pair. But this means that if you're using MLChem in that protocol we were just looking at in figure 4, you can get away, if you only use MLChem in that protocol, you can get away with not including the encapsulation key into your protocol key schedule, because you know that MLChem always binds that in. This is the nice thing you can get, is if you have like a protocol that's like tightly designed around its primitives. But if you don't have a protocol that's tightly designed around its primitive, like kind of your TLS and maybe your SSH and some other stuff, you have to be a little bit more conservative. You don't know if you're going to always be using MLChem. You might be using something like RSA SVE, or I forget, I wrote a whole blog post that includes the classic release and the failure of the binding rules, and I forget exactly which way it fails to bind. I think it's a ciphertext. You can't rely on that. So you have to include the public information, including the encapsulation key and probably including the ciphertext and anything else you need for the rest of your protocol, which is a little bit more hashing, which may or may not be expensive for you depending on what you're doing with your protocol. But yeah, like this shit matters. Chris says, I feel like TLS and some other protocols expect to get access to the raw secret out of the chem. Yeah, except TLS does a bunch of other shit with that raw secret. Like it gets shoved into the TLS 1.3 key schedule, the same place that the elliptic curve Diffie-Hellman shared secret would get shoved. And there's a whole bunch of other like key schedules and domain separated and labeled extract and expands with HKDF. It's really, really nice. We were able to get away with the simplest way to do this in TLS 1.3 because the TLS 1.3 key schedule is just really nice, and it just has like a bunch of belt and suspenders that's quite efficient, that saves your ass from weird shit like this. So you could do classic McAleese in TLS 1.3 even though it's kind of huge, and you probably could do RSA SVE in it as well, because of the other stuff that TLS 1.3 is doing for you. So we love TLS 1.3 in this house, don't we, folks? Anyway, I'm going to go back. Yeah, so that's that figure. And then I'm going to skip over the static ephemeral because I need to get to the RSA bit. I mean, it's totally doable. It's just, actually, there's a little bit of debate about, well, HKDF expand is officially a Nist KDM, I think. They have some document somewhere that's like, yes, HKDF expand is like totally checks off some Nist requirement. And then there's like somewhere else where the whole thing, HKDF expand extract, used in a particular setting in a particular way, is also a Nist approved thing. I think Filippo Valsorda wrote a whole post about this stuff because he's been going very deep into getting Go's crypto stuff FIPS certifiable, which is like a whole massive effort. So I think he has the specifics, and I think specifically Nist has Nist labs will validate they'll do their cryptographic module validation, program validation of TLS, and specifically TLS 1.3, and like you can go through the software modules that they have validated, and it includes explicitly like TLS 1.3 like key schedule or key agreement or HKDF or whatever, and it's basically like at least in TLS 1.3 HKDF after you do elliptic curve Diffie-Hellman or you do any kind of key establishment is basically like good, because RSA is still supported as like a key agreement thing, I think, somewhere else. TLS 1.3 as at least, and I forget if it's in TLS 1.3. So at least in HKDF, in TLS 1.3 is FIPS approved because they will certify it. All this shit is fucking confusing. A lot of people look at all these pieces and want Nist to just be like, can you please just put out like yet another document that's like, yes, just you can use HKDF full stop with like extract and expand, and just like make it explicitly clear that this is a Nist approved KDF or KDM or, you know, whatever. Yeah, it is fine. It's all about Nist, like, because people spend so much time and effort and money making sure that like whatever thing that they build is theoretically FIPSable, so they can theoretically sell it to the US government or anyone else that depends on FIPS. Because at the very least, if they are one of your customers in theory or in practice, you either have to build two things. You have to build a thing with like a FIPS configuration and a non-FIPS configuration, or you build one thing, and then one thing is easier to maintain than one thing with multiple configurations, or two things, or, you know, whatever, or you don't care about FIPS. And so a lot of people try to like really make sure if they care about this, that they're not going to spend like time and effort and money to get something FIPS validated that can't be FIPS validated, because they might have to go back and rip it all up and do a security analysis and shit like that. And everyone, even Nist, agrees that like HKDF is great and fine. And like, I know there's a lot of other people in the US government who like, they have a bunch of SHA-2 hardware and they like HKDF because they could still use SHA-256 hardware without having to do much work. They can just, you know, do it via HKDF and it's fine. Whereas now we have MLChem and you've got SHA-3, and that's a whole different function and it's a whole different design, and there's no SHA-2 in there. So like, anyway, it's all just FIPSology and crap. So I'm pretty sure it's not about security. Everyone agrees that the security is fine. It's about compliance and being validatable as compliant. So yeah. And another unfortunate, this is the kind of thing I think I talked about on the last part. Shot the reason. Yeah. And for CNSA 2.0, my strong suspicion is that they just have a ton of SHA-2 hardware. So yeah. And they do not have SHA-3 hardware. It is a big FIPSy mess. It's a kind of a Nisty mess because, yeah, it is. Yeah, Fire is gonna encapsulate with EK. Right, static. Okay. Keygen. Okay, sure. Yeah, like this is, I'm pretty sure in the both the hybrid and the MLChem only proposals for TLS 1.3, it's all ephemeral. Then there's like Chem TLS, which is like a different kettle of fish and a big thing, a big different thing. It's just kind of like gone in the fridge for now. Authentication, some check is required. Okay. Confirmation derivation. Some applications use shared secret directly as symmetric keys. Yeah, and like they designed FIPS 2.3 MLChem explicitly to allow this, even though kind of good protocol shit. Friends don't let friends KDF without domain separation. So like even if you that's another thing, especially because there is domain separation within MLChem between, it uses a different XOF, it uses a different thing to do keygen. It has many different hash functions. They're value secure PRFs in all their different places. But it's hard to domain separate outside of like a whole thing you can control. So like you have SHA-3 in here, and like I'm a co-author on X-Wing. X-Wing is a hybrid chem. We use SHA-3 too. We have a SHA-3 that's the KDF or the hybrid chem, and then inside MLChem, which we use as a component, there's more SHA-3 happening. The outside one in X-Wing is domain separated. We have a fun little piece of ASCII art, and the one inside is not. And I know that we can kind of do that because we see more of our larger protocol all the way down to the guts of the component algorithms. And I know it's hard for yes. Yes, bunch of nerds. What was I going to say? I was already saying something. Yeah, I know that like if you're FIPS, it's really hard for you to like meaningfully domain separate your use of SHA-3 from all the other uses of SHA-3 in the world. But you could do something like kind of good faith, like kind of just like something, just a little something. So if you kind of do it in here, I think it's like, is it G or J? That are actually, yeah. So G is SHA-3, J is Shake 256, and H is SHA-3 256. Oh, SHA-3 512. Oh, that's funny. I forgot about that. Huh. So I think it's one of these is, I think J is extracting more from this than the honest one. That's funny. G and J. No, okay, never mind. It's the other way around. So, okay. And J is Shake? Huh. I'm just realizing that. J is Shake, which is like the failure mode of the FO transform of the implicit rejection. And G is the, correct mode. And that's SHA-3 512, and this is Shake. That's funny. Anyway, okay. So also, I think this is the only usage of SHA-3 256. You could just domain separate this. You could just have C, your pre-image, and just like concatenate, something here. Like, I don't know, like not X-Wing. MLChem 512, 768, 1024. Like you could put some stuff in there so that it's not just raw. Like you could do something, but Nist just doesn't seem to like to do stuff like that. And like I bet someone could make a strong argument that that's not super meaningful. Yeah, but there's hashing and pre-hashing, and yeah, I do like that they put the OID in. I think that has to do with like the hashing and the pre-hashing and having to identify which one is which. And here it's like there is none. I'm pretty sure they don't even. I think so. One thing that's very clear is that Nist definitely did domain separation by lengths and sizes, which is valid. But so like everything in the different parameter sets, everything is like differently shaped and differently sized, which is good, and especially within all the functions they use. But yeah, in MLDSA, I think they don't have as much of that, and also they have different hash functions, and they have to identify which one is being used for pre-hashing and hashing and the message and all that sort of stuff. I think that's what that is, but I haven't looked at MLDSA for a minute, at least a couple of weeks. But yeah, if I ran the world and I was dictator, I would just domain separate and just put in a label in all these hash function invocations, no matter what. And then some people might be like, that's extra, you don't need to do that. And I'm like, it fits, especially if it fits in a Keccak block. I would make sure it fit. It doesn't impact performance. It doesn't impact, overflowing the block and impact hardware performance. And it's just like one little more kind of belt and suspenders sort of thing for protocol analysis and that sort of stuff. But I am not, benevolent dictator of Nist or, Deirdre's private standardization body, nor do I want to at this time. Yeah, okay, confirmation derivation, la la la. I don't love it, but, for bare bones security of the key, all right, that was one of their goals. For other applications, Alice involved might need to first post-process this can be appropriate and then use the results input. Yes. Yeah. Post-processing might include confirmation. Yeah, that's what protocol in Figure 5 is doing to confirm that KA equals KB and reject them otherwise. Sure. Might also, this is basically them doing a MAC with a partial, a subset of the shared secret value and then checking the MAC. And it's like, yeah, sure, all right. That's a way to do it. But you still aren't binding to the public key. They're the encapsulation key. You still have that vulnerability even when you do that. Because it's completely determined by the shared secret whether that MAC will pass. And that shared secret is not bound to the encapsulation key for RSA SVE or another weakly binding Kem that does not bind, like whatever, like star bind K PK in the parlance of Kramer's paper. Yeah, it might also include key derivation steps to securely produce multiple symmetric keys from the initial shared secret key, like TLS 1.3. They kind of use it for different pieces. In some cases, key confirmation might also include performing additional computations during the encapsulation to encapsulation stages to produce another information rounds. Interesting. Okay. I think I skimmed this before. Key derivation. Oh yeah. I'm pretty sure this is like this is them like citing reproducing their stuff from SB 800 108 and then maybe 56, maybe 133, I don't remember, where K concat Z and then later we're gonna see Z concat like T or whatever is a sort of like, you can just like shove a bunch of extra crap in here and that will, as long as like the actual like key, like the K here that you're shoving into the Nist approved KDF is derived from a Nist approved key generating thing like MLChem or whatever, like something that got spat out of one of the FIPS 202 things. You can basically do whatever you want. And this is basically where the Nist compatible hybrid post-quantum traditional stuff revolves around, because like as long as you put your either MLChem or your P56 secret in this position, you can put whatever you want in the end, and it can be classical, traditional, it can be post-quantum, it can be weird, it can be like putting all your protocol information and all that shit in there, and that theoretically is Nist compatible. There's two definitions of it, but it's kind of the same. I think this document is the one that says, actually, like, you can put it in wherever position you want, because people were like, dude, I could put my P56 secret in the Nist position now and put like MLChem after. But that is FIPS now. But in like 5 to 10 years with the timeline saying, oh no, this is going to be deprecated and then disallowed, then it won't be anymore. And that's a pain in the butt. I would love to be able to just like ship that right now, which I can theoretically do, and be like, yay, I am FIPS approved, and I can sell you that product. Putting MLChem first and SecB56 second is like long-lived, but it would take you time to get that construction, that brand new construction, validated by a lab, by a CMVP lab. And there are only so many labs, and they have only so many staff, and there's a line, and there's a waiting list. And if you feel much more confident about your putting P56 first than putting MLChem first, or making that change, like maybe you already have something working like that and it's like an easier change, you would rather not have to do that. I think this document is finally saying in like the next 2 pages, you can put it in any direction, but that's not how it's traditionally been. So there's still going to be like, this is still a draft. So it may change between like there's having a workshop in February or something like that. So it's going to be at least several months until this is final. It's possible that it will change. But yeah. Chems, on the other hand, by definition, output a key that is ready to use. Say SVE and other chems, they vary by ready to use. Key duration is not required in using chems. I feel like that is bad advice. I understand why they are saying that, but I would not agree with that. Some applications using chems will require key duration. Yes. For example, shared secret is expanded to create a collection of keys. Yeah. Specified in SB 800-108, key duration consists applying a key duration method to a key duration key. Method is now transforming given key duration key and some other data into keying material, such as a list of keys. Concatenate method is concatenate the key duration key with option D to Z. Apply a key derivation function KDF. Yep, just shove that through your KDF and you use the output. In 56C, several key derivation methods are defined for the setting in which the inputs to a key derivation key is a shared secret for one of the key establishment keys specified in 1 and 2 rather than the caveat. Yeah. This is where we're jumping off. When the key derivation for a chem pi is needed, the shared secret output by pi as in an output of NCAPs or DCAPs may be used as a key derivation key supplied to an approved key derivation method specified in SB 800-108, SB 856E, or SB 800-133. In the case where KDM from SB 856 key is used, the shared secret of the chem is used as an input to the KDM input or shared secret. Okay, fine. Yep. Section 2. Nope, we haven't done that yet. All right, key confirmation. That's where you're using the MAC and all that shit. Changing value can only be calculated correctly with high probability if the key establishment is successful. Yeah. I also think that requiring KDF is a mistake. There's too much risk of people reusing shared secret into different ways. Yeah. Like if they updated this to say, if this said you can use MLChem, the shared secret spat out from MLChem without also putting that shared secret through another KDF, a Nist one or whatever, I would probably feel comfortable with that because that was designed specifically with that kind of goal in mind, that you could use it, including when the implicit rejection fails, when the decapsulation fails and all that shit. It's not fully domain separated. It's not totally binding to, it's when you use the seed variant for the keys, you're in pretty great shape for the binding properties of MLChem. It's not 100% perfect, but it's pretty great. I would feel comfortable with, I wouldn't be worried. I'm worried about using any generic in CCA chem the way that this language says. I would look at the rest of your protocol and be like, you're doing all this protocol shit, and I think you should probably be using, a specific KDF for that. But them saying, you can use the shared secret spat out of MLChem, a correctly, implemented and not shit MLChem implementation, I would be like, yeah, all right. But any other random thing, like especially because they found this DH chem and RSASV chem in their other Nist documents, and they're like, oh, look, this is a chem. And it's like, yeah, it is, but it's not. I doubt that it was designed to be used the way that you are recommending it be used here. But I don't know. I don't like it. I don't love that. This is funny. Key confirmation should be used during chem usage. Definitely won't accidentally position or say chem. Yeah. Enhance the security property of may. Confirming successful establishment of shared secret can also address potential errors. Yeah, I guess. I need to go double check what TLS 1.3 does here. If they're macking the shit out of stuff. I don't know if they are. I don't remember. They mac some things. I forget. This is various ways. Shared secret for authenticated encryption can act as a key combination. Yeah, that's true. But maybe they may. Bleh. I think. What are you allowed to use? You're allowed to use AES GCM, Cha-Cha Poly with 1305. I think you're allowed to use AES counter, HMAC 256, SHA-256 in TLS 1.3. And so if you use your shared secret spat out and you use like part of the key for the authenticated the additional shit and use the other one for the like actual encryption, if you're able to do your authenticated encryption successfully, then that's doing this key confirmation shit that we will see in figure 5, just kind of implicitly. Yeah, I prefer that because you should be using authenticated encryption for your symmetric shit anyway. Yeah. You forward foreign key confirmation, including dedicated key confirmation steps into a key establishment scheme. Method below. Okay, yeah. Sure. Yeah. This is constructing your MAC data. Yeah, I think I went over this time. Yeah. You split up your key confirmation key and your data key. And so you wouldn't quite do this. You would do your, AES-GCM style, or you would do your Cha-Cha Poly 1305 style, or whatever you're doing. There's probably like a hot and sexy, like context committing authenticated encryption mode that Sanketh knows better than I. That's not coming to me, like OCB or OCSIV or something like that. That's probably the new hotness. Yeah, and then derivation function not used. The template is okay. Yeah, AES hot sexy. I don't know how you backronym context committing encryption, but I bet we can figure it out. Okay, and this is similar protocol to figure 4, except it's doing this key confirmation shit explicitly. So you take your shared secret from encaps, you put it through a KDF, you get your key confirmation bits, your data encryption bits, you do the MAC construction that we saw up here, way up here. And then you MAC over that data with the bits that came out of your shared secret just for that. And then you attach a tag to the message. You include your ciphertext, your tag, the ID that's going into the MAC data, and then this extra B crap that goes into the MAC data. You do your decaps, you get your shit, you reconstruct the MAC data, you verify the MAC tag over the MAC data you constructed with the key material from the beginning of the shared secret. And if it verifies, you continue. So if you can probably tell that this still is completely dependent on the properties of the chem scheme itself. And that if this shared secret does, like, if you look at all the data that goes in, there's a label, there's an identifier that they send you that's public. That's good. There's other identifiers. There's like ephemeral data provided. This is public. Where is it? I'm not even sure. That might be optional. And there's extra data that's all public. So that's all public and visible. And any attacker can just copy that. So this is all dependent on whether this actually passes, and it will pass. this is all independent of, well, it depends on the chem, whether it's independent of the encapsulation key or not. Same as the other one that was not doing key confirmation. I'm gonna skip forward. And now we're gonna get to the hybrid stuff. I think I did a little bit earlier. Hey, X-Wing mentioned, yay, drink. Migration to post-quantum, for example, might initially include multi-algorithm. Yeah, initially, not forever. Include multi-algorithm solutions, combine one new post-quantum algorithm with one tried and trusted but quantum vulnerable or traditional algorithm. Excellent shot. Yep. Sometimes referred to as a hybrid. For example, X-Wing is a hybrid chem built from two components, MLChem and X25519. It's also explicitly taking the HBKE DH chem style and kind of completely inlining it in. So it's not just you're doing an elliptic curve Diffie-Hellman and just like shoving that in there. It's trying to take, you have a long-term public key pair, and then you have an ephemeral key pair, and you do the shared secret, you do the Diffie-Hellman, you have the shared secret, but you're also shoving in the ephemeral public key, the long-term public key, shared secret, and then DH chem, you have a KDF, and then you use that to actually spit out the chem shared secret. We're inlining all of that into SHA-3, and then also into SHA-3 goes the ML chem shared secret, and my co-authors prove that when you use ML chem specifically, the collision resistance of the design is specifically resilient to attacks against quantum computers because of the security of the guts of the thing. And this means that we don't need to include the encapsulation key and the ciphertext for ML chem inside X-Wing. But that's not necessarily true for any other post-quantum chem, even any other lattice-based post-quantum chem. You have to, it's all about the internal gut specific of the component algorithm, about whether you can get away with that or not. And I think we show that if you use the seed form of X-Wing, which is the current version that we specify in our IATF document, you have good binding properties for the hybrid chem. And you go into the guts of the game of how to do that. It's pretty good. I think it's pretty good. I think we have malbind K stuff for part of it, but we need to update that. Combiner. This is their recommendation for constructing a composite chem. And here we go. Most key establishment schemes of interest can be easily adapted to chems. ECDH chem and RSA chem, which is in the next section. Over the hybrid PQT applications calls for two component schemes, one post-quantum, one traditional. Described below is easily adapted to other cases, such as combining more than two schemes, or combine chems with non-chems. Yeah. And the encapsulation key is just concatenating everything. And then yes, key combine. And what do they define for key combine? For some reason, the focus on combiner really bothers me. The whole thing is the scheme. Okay, this include the shared secrets, the ciphertext, the encapsulation keys, and the parameters. Great. Whatever this is, it's supposed to be a secure PRF, something you would use as a KDF. Maybe P includes a label. Love it. That literally, like, you can practically use it for any, half decent in CCA chem, including the shitty RSA chem, because it doesn't bind, the RSASV chem that they mentioned that we'll get to doesn't bind to its encapsulation key, but your hybrid combiner, your hybrid construction is binding to it anyway. And similar for the ciphertext. So it's pretty good. Feel you need to take a shot every time they still allow what you say. Yeah, they're being explicit that it's going to be the words deprecated in like 5 years and then like disallowed in like 10. But in this document, they're like, here's another chem, and like, I don't know. At least making an example of the thing you can use in a hybrid fashion. So like, I'm quite happy with this. I'm happy that they literally were like, wait, and then the question is key combined. So yeah, like, it's actually pretty great. This is, I have a document out there, and I literally called this thing kitchen sink. It's conservative. It's practically bulletproof. It's not the most efficient, but like if you're doing this, like, and you don't know what necessarily all the components are that are going into it, this will be secure to use no matter what. So yay, good job. And then we look at key combine. Yeah, and since the inputs to key combine include the composite encapsulation keys, the decapsulating party must retain a copy of that key. But yeah, it will be able to recreate it from the seed. Yeah. Can be extended. More than 2 components. Yes, you can. And yeah, that may come in handy for multiple post-quantum hybrid things. Okay. In those cases, okay. Still, most multi-algorithm schemes will likely include a step in which a series of shared secret are combined via the key combiner algorithm of form similar to key combine above. In those cases, yeah, okay. Key combiner, some key derivation methods approved in SB 56C. Key combiner approved in 133R2. This is interesting because they still aren't mentioning FIPS 202 and FIPS 203, which is MOChem, uses a KDF from FIPS 202, which is Shake and SHA-3, and like they're still not okay. And minimum key combine accepts 2 shared secret as input. Optionally can accept additional information such as ciphertext, encapsulation keys, parameter sets, or other context-dependent data. Yep. And then it outputs the shared secret key. Let's see. Derivation methods. Key combination methods. Okay, 56C. 56C. Derivation method is applied to a shared secret. Yeah, so this is the thing I mentioned before. Z concat other inputs. Or Z concat T or whatever. This is where a lot of the hybrid stuff is like really leaned on. Applied to a shared secret Z generated specified in 856A or 856B, along with some additional input. Is this the like approved RPGs? No, okay, no, it's not. It's the yeah, 56A R3. Okay, this is like elliptic curve shit. And 6B, nope, 33, nope. Oh, RSA. This one's for RSA. Okay. So this is literally the like use elliptic curves and like use the approved thing from those ones with the elliptic curves or RSA. Put your post-quantum shit in here. Twisty maze of specs. Yes. All the FIP shit is a twisty maze of specs. And like to a point IATF is too, but like at least like I don't know, feels a little bit different. I don't know. Can take 1 of 2 forms. One step key derivation could be by applying key derivation function KDF to concatenation, or 2-step. Yeah. So this is the extract expand. This is like the HKDF style, and I guess you could make an argument of like absorb and squeeze is similar to. Extract, a randomness extractor followed by expand. So like, if you're familiar with HKDF, like, look, it's HKDF. And then, you know, the extract is putting in the shared secret assault, and then that is shoved in with other input. And if you want a cool example of this, 3 iMessage. This is exactly what the updated version of iMessage with post-quantum key agreement they updated their ratcheting, and I think they're the first ones I've seen actually deploy the split PRF construction. I think because they were already using HKDF this way, and they were like, we can make this work. Oh, this is that's the wrong one. Yeah, this one. Yeah, here we go. So this is actually deployed in all modern iMessage. Then like all in one is like extract. You shove out the extract and then you pass all that stuff into expand, and then you output two different keys. There's like a ratcheting key and I think like a chaining key. I forget, because they actually introduced ratcheting into iMessage when they made all these updates, which is pretty great. You shove in one of your shared secrets, like say P56-1, as the like keying material, and then you put in like, I think it's your previous root key. Okay, root key, chain key, sort of like the previous state key. Oh, you get this. You shove that. Oh, if you don't have another one, you extract. Rather run expand twice than split the output. You mean down here? No, I think they don't want to split the output. They want the whole thing. I think they want the whole thing. Yeah. And they get like 512 out of it. So I think that's fine. Yeah, so and then like if you have another shared secret, then you do a different extract with the nuke thing as the keying material there, and then with the shared secret another two over as the salt. And this is part of the split PRF like assumption that was shown to be secure, or was proven to exist here for this construction. You can do this here. You can't necessarily do it with all KDFs that look like this. Performance is something they're worried about for iMessage. Yeah, they only run. Yep, exactly. I forget if they ratchet every 50 messages, but they definitely do updated post-quantum share. Only 50 or so messages or like 7 days or something like that. Because they establish with MOChem 1024 kind of like the signal style ephemeral pre-keys and shit like that. It's all hybrid. So they have P256 stuff and they have MOChem stuff. And they do that for the session setup. This is like what Signal update is to as well, except I think they're still using X25519 instead of P56. But then the thing that iMessage does on top is that every 50 messages or 7 days, whichever one comes first, they do yet another, I think, MOChem 768 and mix that into the ratcheting keys as well. So they're updating their post-quantum security every 50 messages or 7 days or something like that, which is pretty cool. I think they're the most post-quantumous, messaging protocol out there at the moment. It's pretty cool. Yeah. These are nice. The one I'm looking at, this is Douglas Stabila. This is his pen and paper, proofs and modeling. And then the other one that I had open first is doing a bunch of proofs in ProVerif. And I forget exactly who worked on those, but there's like, they definitely hit it from different angles, which is pretty nice. Yeah, and then so we get the other extract, which relies on the split PRF, and then finally we do our expand, where we take the output of that second extract as our key material, and then we have a bunch of labels, and then we get 512 bits out, and then we split that up into our root key and our chaining key. Let's see, no, pretty sure. Yeah, I forget if it's which exact assumptions that. I'm pretty sure it's this split PRF thing. but maybe they just call it something different. Let's hear it. But yeah, like they are the ones that I'm aware are doing it that way. You can kind of squint at TLS 1.3 and kind of say that it's doing something like that too, and it's been doing it for a while. But it's like they do an extract and then they do like expand, and every single one is like a labeled like, okay, this is for this part of the handshake, and like they'll have like an expanded out that's for the client side originating traffic, and then they'll have a different one for the servers originating traffic of the handshake, and they're splitting it up. And I forget if it's kind of doing something similar to this, which is like it's taking keying material from a previous extract and other keying material, and they're putting the other keying material into like the salt area or the other input area or whatever. So they're kind of using both of them, but they're slightly different. I don't know if TLS 1.3 is doing that specifically, or if they're just chaining, taking like key material from an extract or a previous step and just putting it into the same key material spot, and like everything in the additional data or salt or whatever is salt or literally just like label information. Yep, exactly. Expand with different labels or changing expands. Yep. I think that's the very common usage pattern, and this sort of split PRF assumption of like putting secret material in different places and like, is that secure? I think that's very recent work in like the past 2 years or so. So Apple adopting that for their post-quantum upgrade to iMessage was pretty cool to see. And it's especially if you're using HKDF already, it's kind of a nice, like, you can just kind of slot that in there and like win-win, as opposed to kind of trying to re-architect. Like one way you can really do it is just be like, concatenate your shit and just shove it into that key material place. Like that would be like the first thing I think to myself. But this is cool too. I don't know if other people will like be like, yeah, I'm gonna use this like to extract and then expand kind of dealy, but you never know. I think it's pretty cool. Okay. And then yeah, so that's the shit here. It's required the extraction is applied to the shared secrecy. Yes. Always shove in the KDF, like you sorted it out. I mean, yeah, shove it in the KDF, label it, either concatenate the label or put it in the appropriate place in the KDF, and like at the very least your formal analysis of the thing is not going to find like, oh, I can take this thing from over here and this other invocation of this oracle and shove it into this other one, and like, ooh, look at that, I have an attack. Like you won't have, at least you will not have that. And like, yeah. Okay. 56C describes the specifically approved choices: KDF, extract, expand, as well as the format and context. Do I have 56C open? Pardon. 56B. 56A. There are too many. There. Yeah, I've opened this before. So, yep. Under 108 shall be used a key expansion. Wait. Extraction, then expansion. Okay. Okay. Use a MAC. Implementation of HMAC based on approved hash function, which sounds like SHA-256 is. So I think this might say, if you know what you're looking at, that HKDF based on SHA-256 is usable. It's just a matter of like making sure you'll get validated by the lab if you care about that. Or CMAC, yeah. Untruncated output of the MAC algorithm is used as a key diversion key for subsequent expansion. Yes. PRF based KDF. Okay. Shall be used for key expansion. Prove MAC algorithm as the PRF. Okay. PRF used by KDF for key expansion. Okay, yeah. Okay. Yeah, this is fucking... If it walks like an HKDF and it quacks like a HKDF, it sounds like you're fucking talking about HKDF. Much other extra shit. course, they're not gonna fucking say that. Yeah, SHA-36. Great. Yes. HKDF. Okay, I have to remember this. Sounds like it's literally, like, I don't know why this is controversial then. HMAC based KDF, we don't like to see. Yeah, yeah. I mean, they specifically cite it, but like, sure, whatever. That's funny, because now we have to go double check with some people. It's like, how is this not super duper explicitly, transparently clear? Why is this even a question? Okay. This publication approves the application of these KDMs to the shared secrets of the approved Kems, including the quantity Z. It can be the shared secret of Chem. Yay! Very good, yay. And then this would be your traditional shit, if you want, which I think is the correct way to go. It'll future-proof you even if it's going to take you there. Thank you. Okay. Yeah. Good jobbies. Okay, and now this is a key combiner, which is different than the other thing, the extract expand thing. One step, two step. 56C allows the shared secret Z to have form. Yeah, concat S1, S2. Yeah, that's what we were saying before. Just concatenate the shit out of that stuff and shove it through. She does. She's had a little bit in there, but needs a refresher. So it sounds like at least Nist doesn't like it, doesn't want you to concatenate your shit and then put it through here. They do not want Z to be your concatenated MO-Chem shared secret and say your, you know, your elliptic curve Diffie-Hellman shared secret. They want this to be your MO-Chem shared secret and your other input to be your Diffie-Hellman shared secret. But for this thing, they do want that to be the one-step thing, which is basically SHA-3 and other stuff. Sure. Yeah. Yes, you can combine many shared secrets. Okay. This publication approves the use of the key combiner 14 for any T's greater than 1 so long as at least one shared secret is a shared secret generated from the key establishment methods of 56A or 56B or an approved Chem. Or an approved Chem, okay. Important to note that in the case... So, okay. Okay, I'll get there. Important to note that in the case where the KDM in the combiner 14 is a two-step, extraction is performed with all shared secrets input. What? This is confusing. Let's just be... Okay, it's just a method. Extraction expand. So it does let you. Never mind, alright. Fine, sure. Like, I guess I have to go look at the sort of split PRF analysis to see if there's any, like, meaningful difference between concatenating the shit and just shoving it through, or doing the kind of iMessage style. I have a feeling there isn't a meaningful distinction, but I don't know. Maybe I'll go read that. 56C allows other input to contain an input that is chosen arbitrarily. Contain the parameters. Okay. Choosing fixed and fill appropriately, we can construct approved key combiners of form 14 that, in addition to shared secrets, also receive additional inputs like encapsulation, key ciphertext parameters. That's advanced. Yep. Choose the KDM to be the one-step key derivation method with KDF as hash function H. Sure. Jesus. 56C R2. Do you even mention SHA? I can type. Okay, they do. Alright. Oh, no, they do. Okay. There's too many documents, man. Too many fucking documents. I guess they specify it in FIPS 202, and then they talk about what's approved usage in these other 56 ABC. Alright, so you can use something like SHA-3. Set other input to contain only the concatenation of ciphertext, encapsulation keys, and the parameter set to define the key combiner, blah, blah, blah. Okay, then, yep, that's the one we saw before. Can instantiate the composite Chem example from 5.5 by using the key combiner. Yep. Composite Chem with shared secret whose length is the output of H. I'm worried that the way that this is written, people won't necessarily use this. But they might use this, and this, and this, which is not, well, the way they wrote it, if they're not stupid, if they actually just, like, connect the dots, if they just replace the other thing with this thing. Okay. Oh, gosh. 800, 133. 3 improved methods for combining cryptographic keys generated by approved way. Concatenation, XORing, key extraction, KMAC. Just concatenation says no to say better. Yeah, but if you're reading this document and you're like, oh, what are my options for literally this function key combine that was mentioned up here? So far, they've only mentioned one, which is this one. But they mentioned all this other shit that looks similar. That is not a great hybrid chem combiner, in my opinion. So I'm just a little bit worried that people are like, I'll do that, and that will be my key combine. And if you read closely, that's not what it's saying. But I am worried that it's just sort of like, yeah, you might be right. Yeah, and that's aligned with some of the major recommendations from other papers. This is probably citing from or inspired by. Some of these methods can be applied as just a single key. Is it? These methods can be thus used directly as key combiners or constructing multi-row schemes. Yep. Okay. Considerations for composite schemes. Yep. Chosen plain text of tax security. Chosen ciphertext tax security. Well-constructed composite chem should preserve the security properties of its component chems. Depends on how the composite chem is constructed, and particularly on the choice of key combiner. Yep. They don't mention binding properties at all. In the case which goal is active CCA security, but only one of the two schemes itself is NCCA. Got around. Yeah, no problem. Thank you. Thanks for joining chat. Yeah. The designer of the composite scheme does not know which one it is. Sure. Well, the whole point is that at least one remains secure, and you want the construction to still retain security when one of them is broken. All but one are broken, such as by a quantum computer. Shown in 25. I don't want to click away. I want to lose my spot. The straightforward key combiner KDF concat the shared secrets that only uses 2 shared secrets does not preserve NCCA security. Thank you. The scheme Pi 2 could be so broken that the combined Pi 1, Pi 2 is not NCCA, even if Pi 1 is NCCA, and regardless of KDF is used. Yes! Very good. Therefore, Nist encourages the use of key combiners that generically preserve NCCA security. Very good. It also preserves other things. Such a key combiner as follows. Let each hash function prove for most of their key administrations such as SHA-3. Key combiner as follows. Gosh, yeah, sure. Yes, the two keys, the 2 ciphertexts, the 2 ephemeral encapsulation keys, and the domain separator. Look at that! Yes, uniquely identify the composite scheme. What about the parameters? I don't know, fuck it. Okay, maybe it includes the parameters. Use equally, e.g. Pi 1, Pi 2 order of composition, the choice of key combiner, and the KDF. Love it. That's it. Oh, God, I love that. Security practice. Well, composite schemes are meant to increase security, necessarily add a layer of additional complexity to the basic chem framework. Additional complexity will be reflected in the implementations and applications to introduce security vulnerabilities. Moreover, adding composite schemes introduces additional choices in protocols, which should also introduce vulnerability in the form of downgrade attacks. Yes, implementers and users should be aware of the potential challenges in implementing and deploying composite schemes. Oh, sweetie. I'll be right back. Hold on. Fussy girl is my guest. Killing me. I'm trying to comfort you, and you're eating everything. Okay. Nope. Shush. So far, I'm quite happy that the only explicit combiner is the one that's kind of bulletproof. need to stop. Okay. Section 6, examples. No requirements, just specific guidance. Aid the reader in understanding some aspects of Kems are constructed and used in manners consistent with Nist guidance. Examples of Kems. 3. ECDH Chem, not to be confused with DH Chem and HPK, RSA Chem, and ML Chem. While ECDH and RSA features are perhaps not typically described as Kems. The goal of these descriptions. Oh, stop. Illustrative only. I still don't love it. Episode 3 already contains a complete description of all Chem. Yeah, okay. Chem from Diffie-Hellman. Yep. Have a long-term key pair to encapsulate. Output is the key derived source of material on the subjects. I've read this and I'm pretty sure it's exactly just like you have a long-term key pair, Diffie-Hellman key pair. You create an ephemeral key pair that's kind of like the public key is your ciphertext, and then you do your Diffie-Hellman with the static key pair and the ephemeral key pair, and the the ephemeral your encapsulation key is the static one, and your ciphertext is the ephemeral one, and then the shared secret is the shared secret from Diffie-Hellman. And the way that they define it, they don't have a KDF at the end. They just have the shared secret, which is not the best. But because of the properties of the curve Diffie-Hellman, and the curves, they're not specifying any covector curves. They're all prime order Nist curves, and the compression formats and all that sort of stuff. The bindingness of Diffie-Hellman is pretty good in this construction. It's just I really wish they had like an actual KDF on it, like DH Chem. They don't. They don't explicitly include. They don't explicitly include the public keys, the ephemeral keys, and the public keys, the ciphertext. But they can kind of get away with it, unlike RSA Chem. Nope. Don't try to leap to your doom. RSA, yeah. No, this is your guy. I don't know a ton about the binding properties of RSA schemes, but I'm going to defer to Plaza's email in a second. So this is referencing SB 856B, and it's, yeah, crazy. Section 7.2. They use generate and recover for encapsulate and decapsulate. So RSA EP or whatever, RSA SVE, whatever. I'd literally not heard about it. It's probably just another common form of RSA. It was just a name that's a Nist specific name that I'm not familiar with. Yeah, you encapsulate. Output is the secret value. I'm pretty sure. Yeah, and then there's a nonce for key derivation or something like that. Hey, please. Stop. I know. Please. Yeah. Generate Z, code it. You literally just encrypt Z, quote, the shared secret. It's just like, it's completely not dependent on the public key, and like the commitment to the ciphertext is like I'm pretty sure it's completely independent. I mean, if you vary the Z, you may vary the ciphertext, but not deterministically. Like you will not always vary the ciphertext, I think. I'm not 100% sure, but you definitely don't. If the public key changes, it's definitely doesn't have an effect on the shared secret value. So yeah, you can see that it doesn't have any binding to the encapsulation key, the public key. So, and then okay. Oh yes. Do you want to play with the puppy in the mirror? The puppy who is yourself? Is that what's going on? ML Chem. Talked a lot about ML Chem before. You can go look at ML Chem. Okay. Examples of application of Kems. HPKE. Yeah, yes, you can do that. Sending is this just how do you use HPKE? Huh. Keygen. Send the ephemeral key and parameters. Do end caps. Hey, no. Don't say HPKE and then just like do a like not great version of it. Sometimes referred to as hybrid PKE. No. HPKE is the one that's specified in RFC number, not just hybrid public key encryption. Like, oh, come on, don't do that. I just get very worried when you're writing down protocols in a document like this and that people, and they're like the authors are intending it to be just sort of like an example, but like people go look at this like official Nist document and they're like, cool, I will use that. And they will just copy it verbatim and they don't do domain separation and labeling and all this other good stuff that we've been talking about. And I'm worried about that. But, ooh, sharp teeth. You're silly. Okay, stack, ephemeral key establishment. Yeah. Wait. Yes, unilateral authentication. Okay, is that? That's it. Yay, got mostly to the end. Yay. Approved MAC algorithms, key information. And the generators. The improved random generator. Yep. Nonces. They mention nonces occasionally, like for some of the authenticated MAC authenticated stuff. Like whatever. Okay. So I'm just gonna go back to figure 4, for example. Now that we've looked at a specific example of RSA SVE, which does not bind to the public key because of the way that it generates its shared secret, which is just literally a random value and it's spat out, encrypted and decrypted, completely raw. You are silly. I know. 1 second. Here we are. So if we use that RSA SVE, we spit out our shared secret. It's just a random value. It's just a random value sourced from your random number generator. And then you have some ciphertext. And then you decapsulate your ciphertext using the decapsulation key. And you spit out the random value. So if Eve, so this is the attack that Cass describes. And you can, like, I would fix it at the protocol level because I would be conservative about like just shoving a random chem in there, and you can get other nice protocol benefits out of like including everything in like a key schedule or shoving everything into your KDF, all the public data that goes on the wire. You can get good protocol benefits out of that, whether that's efficient enough for you. Maybe you're hashing in like kilobytes and kilobytes of public data. Like, it's up to you, the designer, to figure out. If you design it very specifically around a specific chem, you might not even have to worry about this. But if you're allowing more than one, you probably want to be a little bit more conservative. So, option 2 requires strongly binding properties from the chems for the example protocol. So, like, I only use MLChem, or I only use X-Wing, or I only use the key combiner that they mentioned, which is like the kitchen sink. That would be fine. Yeah, that'd be better than what exists. So the attack they described is unintended. What do they describe it as? Yeah, unknown key share attack. Because basically, you think that Alice thinks that she's coming to agreement. She's establishing a key with Bob, and Bob thinks he's establishing a key with Alice. But they're both mutually coming to agree on different keys with Alice, or at least manipulated and determined by Alice, and it's not actually binding. The key that Alice negotiates is not actually bound to Bob's public key, and vice versa for Bob with Alice when using a chem like RSA SVE. An example is we assume that these are static chem keys. Sure, why not? It's just whatever. Eve starts a new session with Bob. Bob uses RSA and caps with an ephemera with Eve's encapsulation key. Obtains a shared secret and a ciphertext. Bob sends his ciphertext to Eve because he's encapsulating to Eve's encapsulation key, even though he thinks it's Eve is, quote, being honest. Eve computes, decapsulates to obtain The shared secret with Bob, which is Z. Alice then opens a new session with Alice. Eve generates a new key to be, encapsulates to Alice's static encapsulation key. But instead of using the correct random number generator to generate the secret, as specified in RSA, because Alice is a fucking attacker, so she can do whatever the fuck she wants to choose all her values. Like, she doesn't have to conform to some Nist specification. She uses the shared secret established with Bob, so that she generates ciphertext and the same shared secret. She uses the same shared secret on their side, and then the ciphertext, Alice decapsulates the ciphertext, which decapsulates to Z, which is the same shared secret that Eve computed with Bob, or the one that like Bob computed for her. Alice then sends a nonce to the adversary and incorporates it to the final shared secret K. Is this figure 4? Yeah, sure, whatever. To the adversary and incorporates it into the final shared. It's just KDFing. It's just adding more material. Yeah. Eve learns the nonce because it's encrypted under the shared secret. Forwards it to Bob, who also incorporates it in their final shared secret key K, where you put Z concatenate with nonce through that KDF we were talking about. Thus, Alice and Bob share a key, but Bob thinks it is shared with Eve. The exact same procedure works for figure 5. Keep confirmation step completed similarly because the attacker knows K and can just get confirmation data. You can't do this if with a chem like MLChem, because even if you reseeded the random number generator in MLChem, the shared secret is still bound to the encapsulating key in incaps and decaps. So it would still vary even when Eve is trying to send a manipulated ciphertext to Alice. It's still the same attack could not be used and result in them decapsulating to the same shared secret, with Eve in the middle. Or, Bob thinking he's talking to Eve and then he's actually like being forwarded Alice, or, whatever it is. So that's it. There's some good stuff in here. I hope they change some of the examples. I hope they stop pointing at RSA, SVE. I don't know if they will. There was some chatter about maybe they'll point at some IETF talks instead. Like maybe if they pointed at DHChem in HBKE, it would help avoid confusion and interop confusion. But we'll see. They won't even point at HBKE, even though they're talking about a protocol called HBKE. They do their own thing. But yeah, that's it. I finally got to the end of this. There's some good stuff in here. I'm glad the only key combiner that they actually specify is like the good safe one and not anything more complicated than that. That's great. That matches something in a different document that I'm writing. Okay, me and this little shark are gonna call it for tonight. Thank you all. Bye.